Okay, you wanted to present something? Go for it.
I'll wait a little bit until more people come. I think we wouldn't start. Because I don't know how long yours is going to take, so we don't.
Not too long. Probably not the whole hour. So you can take some time.
see anyone I knew. There's like a Teams call on there.
That's jits. Nobody except blood will want to use jits.
Got him.
It looks like Teams.
It looks like every video we're talking about. And the jits one is important. You
No,
don't
it doesn't look like,
you actually looks like the first.
yeah, exactly. Did you find a flash drive or something?
I'm supposed to know. You already have like 5 hours. More than an hour.
I don't think you can get started. I was gonna show something quickly.
Okay.
Sure. Wanna like start the session? Never mind. I'm not leaving the one.
Sure. Everyone wants to present something that I don't know what it is yet. And then I'll talk about distributed storage after.
All right. Thanks. I need to share my screen. Anyway, so this is something that I don't want to use the word working on because it's like entirely AI coded. But this is a thing that I've been instructing someone else to work on. So it has elements of my design in it. And by someone else, I mean Cursor. Anyway,
How
so
many security vulnerabilities does it have?
anyway, well, it's none because it's not a
Linus,
network.
take your virus system.
All right, so how many of you guys have heard of Anki, like a space repetition in general? So most people, okay. So this is Anki, which is just a web-based Anki client. There is already a web Anki, but it's a little bit crusty, and it didn't have the features that I want, which is basically just a single-page web application that can just save directly to your file system. It doesn't have to go through some cloud service like WebAnki does. So basically, this is just statically hosted on GitHub pages, and it's just a web app, and you can open up Anki decks on it and study them. And then if you're using, well, in either case, you can load them here and then export them back and like save them back over the, like replace the file. Or if you're using Chrome, which supports this thing called the File System Access API, it can directly save on top of the file, sort of transparently. Firefox doesn't support that yet, so you have to do save as. But hopefully that support will come eventually. So anyway, this is sort of what the interface looks like. All AI generated. It did a pretty good job, despite sort of being blind. It's not able to see what it's actually producing. So it looks pretty nice, and it has shortcuts for interacting with it and going through the decks and everything. So you can press space. Just things that you would expect any sort of space repetition system to do. You can edit the decks and whatnot. The feature that I wanted to show off was this was like a thing that I specifically wanted, because sometimes I'll watch a YouTube video that's educational and then I'll just forget everything immediately. And it's sort of a waste of time. So I wanted to basically have the ability to take a YouTube transcript, send it to, say, a self-hosted Olama server or OpenAI if you've got a pro subscription, and then have that generate cards automatically from the transcript, so that it can just, you watch a video, you paste in the YouTube transcript to this web application, and it'll create a new deck so that you can remember the most important things that you learned from that video. So that was the thing that I really wanted, and I've added that into this application. So at home or in EC, I have a workstation that's running Olama with just some like Llama 3.3 or something. Just fits on a single GPU, and this will talk to that. It'll send a YouTube transcript along with this prompt, some default prompt, generate a deck, blah 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 blah, and then it will parse the results back from Olama and convert it to a deck and then insert it into the list of decks here. So I'll give a demo really quick. Let me delete this deck. And so let's say we watched a video about the Supreme Court. You can get the transcript from down here, show the transcript, and like manually copy it. kind of clunky to do it this way. There's also add-ons for Firefox and Chrome that will put a button there that you can just click on it and it will copy the transcript. So that's what I'm doing here. And then we go over to the extras tab, and there's this, like I mentioned, this deck generator extra. Paste in the prompt, paste in the transcript. Let's turn down the number of cards. And then, so that'll take a minute. Anyone have questions while we wait? Or any thoughts or anything? Yeah. Not for space repetition. Oh yeah, I did make an Anki like printable, like you can paste in an Anki deck and it turns into like a printable PDF. I did work on that. That was also partially AI generated. This was like entirely, I didn't even look at the code at all in this.
My favorite would be for them. You should combine them.
I guess, yeah, that could be an extra. Yeah, I have this extras page for stuff like that.
Did you look into using one of the various YouTube APIs to pull the transcript? I don't know if they have that available.
I know that it exists. I didn't really want to do that because I don't want a requirement, so it generated. I didn't want a requirement of this app for someone to create like a developer key and then go through that hassle. So I really tried to avoid that.
Would it be easier to just watch a YouTube video again later?
What is that?
Would it be easier to just watch a YouTube video again later?
I mean, if you want to sit down and watch a 15-minute video again, I guess you could do that. But I think that it's probably better to condense down the information.
YouTube videos are generally very information sparse in my experience.
Okay, so it generated the deck here. Interestingly, we'll go through the card in a second. Interestingly, sometimes when you specify like 3 or 4, whatever you specify a number here, the language model will, the weaker language models will get the number wrong and it'll like generate 5 or 6, even though. So this is not like a hard requirement. I'm just asking the language model to generate 3, but sometimes it will ignore that and generate more. So it's kind of interesting. Yeah. Anyway, so there it is, AI generated. Yeah.
Does it not show the times? Because usually it's just like again, it's 1 minute.
Yeah, I mean, I'm not super familiar with Anki, so I've only been like using this for a few days. I know the Anki has way more features than this has. I was really trying to focus on the YouTube thing, and then also just being able to read the files. Anki file format is kind of ugly. It's like a compressed SQLite archive with some extra files thrown in, and so like getting all that working in a web app is annoying. So that I was just focusing on that stuff now, but yeah, there's a lot of features that are missing, but it has like some basic functionalities that you can actually use, you can study. But yeah, you're right, it's missing stuff. Anyway, that's it. Any other questions? Okay, thanks.
All right. So do I like share my screen here? Is that what I do?
That's right. You all stop sharing.
Mom can see it working. There, it's not surprising. Screen share on the whale is also working.
Okay. Hopefully this works. Okay. Does it show up on the screen?
Yeah.
Wonderful. Does this look better, or does that look better? I don't know. Oh, okay. It was up to I turned it. Okay. Okay. Hi everyone. I'm Sean. I'm presenting on distributed storage today, specifically on CEPH, which is kind of like the open source standard for distributed storage. It's complicated. I tried my best to like distill it a little bit and hopefully like make sense. But yeah. So most of you kind of already get the general motivation, but I figured I'd go over it a little bit anyways. The first like kind of major motivation is redundancy, in the sense of what if a drive fails, right? So not a huge problem if you have like your laptops, your PCs, whatnot going on. Drive failages are rare. But the more data your drive stores and the more drives you have total. And by the way, the context for all of this is like data center-esque, like imagine Google storing all your Google Mail, Gmail stuff, or like your drive stuff, etc. It's more meant for like heavy data usage data centers and not for like personal use. So with that context, what if the drive fails? And I'm gonna pull up this, which is Backblaze is one of like the data backup providers, and they publish this nice little chart of failure rates because they track a lot of both hard drives and SSDs and like analyzing like how often they fail. And it's rare, but it happens, and so you kind of have to account for this in some way, right? And the second important idea is high availability, which is what if the drive fails and you don't want stuff to break while it's failed? Because the obvious idea here is, okay, drive fails, you just have a backup in like some server somewhere, and then you pull out the drive, you put a new one in, you download all the data back, and then you're set. That's not really feasible if you're operating, again, like Gmail, for example, where you're like, okay, drive can fail, I'm gonna spend like a day to plug in a new drive and download all the data back again. You can't really afford that. And so, I don't know if I have, yes. So the thing that you really want is you want your backups and your main data to kind of be in like one system, as opposed to like you have some drives that are just your actual drives and you have backup somewhere else. Because that implies when something from your main drives fails, you have to like pull everything in versus like back out and so on. So this is kind of the methodology that ZFS and a bunch of other like sources use. Here's I think this is RAID 6 or RAID Z2. I don't know too much about ZFS, but they kind of combine your redundancy and your main data together, and that kind of makes it so that if the drive fails, you can quickly switch to a different drive while you're dealing with the issue of, oh, my drive is failed, right? So, for example, if this fails, you have D3, C3, and D3 stored across these, I believe they call them like redundancy partitions or something like that. And then you can still access all your data, and it's also available by the time you're able to plug in a new drive, copy all of them back out into this drive, and then restore your cluster, right? And that's the general idea that, so, and this is like more common for like one server that's just properly doing data redundancy, is you have a system like this where you have multiple drives, a bit more than you need. For example, this is 2 more than you need, I believe. You can take all the blue and put it into maybe 30 blue. I don't know. But the point is you have a bit more than you need, and you're able to split redundancy across all of them. And then if something fails, you have a bit of time to fix it. And hopefully you're praying that like 2 or 3 of them don't fail at the same time, in which case you. So now we get to high availability part 2, which is, okay, but you're Google, you're not like some random home lab person like us. So what do you do if an entire server fails, or the whole rack fails, which happens, less common, but it happens, right? Like racks can lose power, the server can lose power, and you can go further and further with this. You can say, what if my county loses power? And so that's a concern. Sometimes people have data centers in like California and Washington, D.C. and Texas and Illinois and so on, and they split up all their stuff. And you can go as far as you want down this spectrum of like high availability between I don't care about redundancy at all, I have one drive with all my data, and I have servers everywhere. And there's like some compromise you could hit based on like, I know companies have service level agreements and they all try to determine like how much uptime they want and like what they're trying to optimize for. So you have to find some compromise, and some like popular compromises you might have heard of 3-2-1 rule, for example, which is you want 3 copies of your data. I think 2 different storage mediums and 1 that's offsite, which is like you have some level of like you're somewhere along the spectrum. Obviously, you can go further if you wanted more protection, or you could go less. But that's kind of like some recommendation for important data. And so that's kind of the general motivation for like distributed stuff, is that like you don't want all your storage in one location because of issues of drives failing, servers failing, losing power, and so on. So CEPH. Quick TLDR, if you know about ZFS, the best way to imagine it is it's ZFS but across multiple servers. These servers can be right next to each other, they can be across the world, but it's literally taking ZFS and applying network to all the drives. My understanding, and someone who knows ZFS can correct me if I'm wrong, but my understanding is that ZFS doesn't scale that well when it comes to like multiple servers. It's primarily meant for like all the drives in the same server and uses a bunch of like hardware level stuff to do that. CEPH is kind of like the more enterprise like distributed version of it. This is a diagram I found when I looked up on Google CEPH architecture. It's very complicated. I'm going to try to go over it like step by step. You don't have to understand all of this, although I will probably cover most of it. But just like to scare you a little bit before I start. So two kind of aspects you can look at it from is hardware point of view and software point of view. So hardware point of view is literally just you have data. How do you split it across servers and drives and so on in such a way that you guarantee some level of redundancy? And then software point of view is, okay, you've split data across, you're sure that the data is like redundant enough. How do you abstract on top of it to make like stuff like file systems and so on, so that like your stuff is accessible, right? So starting with hardware. I didn't want to put this earlier, but this is kind of going back to motivation. CEPH, I don't know if this is CEPH specific or not, but CEPH at least really wants you to have 3 copies of data. And one of the motivations for that is sometimes you're in a situation where a drive doesn't fail, but a few bits flip. And this is known as bit rot. This is a thing with all drives. Hard drives, SSDs, everything has a little bit of bit rot. I think SSDs are much better at this than hard drives because hard drives are mechanical. But SSDs do have this phenomenon. I think it's when like the capacitors that store your data like lose power for too long or something like that. But the point is that some bits can flip. And so imagine a situation where you have 2 copies of data and then in one copy a bit just flipped. How do you know which one's the right bit, right? Is it the 1 or is it the 0? So that's one of the main motivations here. And that leads to quorum, which is very common in CEPH. And that is when a majority, or in this case 2 out of 3, but when a majority of copies agree on something, we assume that's true, right?
Yeah. Seems like an expensive way to address it.
You can have a checksum, but how do you know which version of the checksum is right?
I know.
Well, I mean, if you're saying the data flips and the checksum flips, then you could say that 2 of the 3 copies flip as well, right?
Who's that?
If you're saying that the data would have to have a bit flip and the checksum would have to have a bit flip?
Well, no, but like you can calculate a checksum for one copy of data. You can calculate a checksum for the other copy. And now if the checksums are different, how do you know like?
Well,
the
the checksums
checksums-
around small. Right?
no, the checksums
Checksums
aren't. Checksums aren't different. They start the same, and then a bit flip somewhere, and then you can compute. But I guess
So you're storing like the correct checksum along with the correct data?
yeah, you got a block level.
What if the checksum bit flips? If, like now your correct data is invalidated.
Well, then you would see your both copies of data in the same checksum.
If you have just one replicate, and you have a checksum of it, and then you just know that it's wrong, and let's say that the checksum doesn't match, you know that it's wrong, but you don't know what the right data is. If you have 3 copies, not only do you know when it's wrong, you also can recover the right data.
And there's also more complicated schemes where you don't need a full duplication and you can get one bit of error and correct it.
Yes.
I'm sure CEPH supports like lots of things.
It does.
Yeah.
Two copies of data plus 2 checksums, then is it like converting because you just
Okay, there's a lot of checksum stuff you can do, is what I'll say. And CEPH does do a bunch of this checksum stuff, but I'll give you one more counterexample, which is, I was going to say this for later, but imagine you have 3 copies of data, and we'll get to later, but they're going to be on like different places, for example, right? So you have like on say 3 separate servers. Let's say you want to like you're a good like cybersecurity person, and you want to upgrade your server. Let's say it takes you like 3 hours to like upgrade the server or something like that. When you have one server that needs to go down, it's also just nicer to have 2 servers to store your data, as opposed to one server that is basically kind of like at the point of like, you know, if that fails, then the end of this comes.
Like
So
additional servers.
it's an extra backup source in that sense. Generally, I do believe, besides this point, 3 copies of something is recommended just because you want one copy for just like doing maintenance on it, and you want another copy for a true backup. Yes, checksums are a thing. I'm just gonna do that one. And then visual representation. It looks basically, this is just like a simple bit by bit comparison. It's just gonna say, hey, two of them have a 0, one of them have a 1. And there's probability behind this too, is like, if your bit flip like rate is very, very low, the chance that you have two drives with the exact same bit flipping is much, much lower than the chance of just one bit in one drive flipping. So you can kind of make this assumption that like if two of them are right, one of them is wrong. So yeah, that's kind of like the 3 copies idea. And the quorum idea beyond just 3 copies of data is also important, and I'll get to that later. Damn, the site's kind of a flash thing. It was called like main point in Google Slides, so but the main point here is that we want to account for both drive failures and server failures. So how do we do that? Well, okay, so we have 3 servers, right? This is kind of like a visualization of how CEPH does this. We have 3 servers, and for now, we assume we want 3 copies of data. By the way, many like organizations and people who care about like very sensitive data are going to do 5, 7 copies. Generally odd numbers because you want like some sort of like agreement between the different types of data. So if it's like 50-50, wouldn't do it. But generally it's like 5, 7, 9, like you'll go on. But for this visualization, I'm going to use 3. Each server has drives. These little white rectangles are drives. I made them kind of like different sized because you can have servers that have like larger drives, smaller drives. You can have servers that have missing drives, so on. So it doesn't all have to be like perfectly like correlated. And what CEPH is going to do is it's going to say, do you want to store like some amount of data 3 times? It's basically random. It's going to randomly take a drive from server A, a drive from server B, and a drive from server C, and put the data into it. And if you have another piece of data, you can do that, and it'll also use another random algorithm to do that. So this kind of relates to like hashing algorithms in the sense of like you can kind of randomly like assume that with such a random algorithm, all the drives are going to have similar utilization, which is what the goal of this is. Because what you're trying to do is, and it takes into account like the size of the drives as well. So if it's a smaller drive, it's going to put less data into it. For example, if it hashes like between 0 and 1,000, it's going to say like the first 50 go into the top left drive, then the next 50 go in here, and
Are
the
you
rest is
hashing
smaller.
file name? So you can then use the file pair for drives around, or do you hash like the data? So that way when you use the file name, you have some indexing.
You hash the data. But also there's a level on top of this where you hash kind of like the block of data as opposed to like the actual data itself.
So it's per block, it's not.
It's per block. These red and orange, so we haven't even gotten to the concept of files yet. The way CEPH operates at the hardware level has nothing to do with files. It's all just like literal bits. All it's doing is, I think each of these blocks, you can change how the size of these blocks, but I think they're like 512 megabytes-ish by default.
So if you store a file smaller than that's efficient, or is it?
It's not inefficient. I'll get to that when I talk about files. But there's a different system that you use for that. So anyways, before I keep going, terminology note. These individual like drives are called OSDs in CEPH land. I don't know why. Technically, the OSDs are like daemons. Think like systemd services or like Docker containers that wrap a drive. So they handle like all the read writes that go on with the drive, and they store a bit of information. So generally, OSDs and drives are kind of interchangeable. Each of these blocks of data are called PGs, or placement groups. And that goes into like how data is split into these placement groups, which I'm not going to get too far into, but there's an algorithm to do that as well. And this algorithm that I'm talking about that like maps these blocks of data to drives is called Crush. And there's a paper about this. Very cool paper. It is actually like worth a read, so I linked it here. But there's actually like a lot of proofs and like stuff about like how the algorithm has to work in order to split data between these drives evenly. And that's kind of like one of the like main papers that brought CEPH into existence, is how it's going to distribute data across drives. So now we have this, but we still need a way to route data requests, right? So you've split data across these 3 servers, but if I want to read some block of data, CEPH has to know in which drive and what location that data is. It can't just like put the data somewhere and not remember it. It needs some way to remember it. And it also needs to route your request to that right location. Right? For example, it needs to route to that service, the OSD service that's managing that drive, saying, I want to read this specific block of data from this drive. And similarly, if you want to write, you have to write to all 3 locations. Because the whole point is replication. So you don't want to just write to one and not write to the other 3, because then your write doesn't replicate. Right? So back to this, I've moved the servers over here. What Ceph uses is something called a monitor. These are shortened to mons, M-O-N. So if you see that, that's also what it means. But a monitor is basically going to like store this entire map, right? It's going to know in some like file in memory or storage or both. It's going to know which blocks of data are in which locations on which drives, basically. And then whenever somebody wants to read, they're going to send a request to the monitors. The monitors are kind of like the public-facing view of Ceph, in the sense they're going to handle all reads and writes. They're going to look at what they're trying to read, where it is, read the data, and they're also going to service writes, in the sense that when you want to write to something or change something, it's going to service that to the proper OSDs and then return back. Any questions, by the way? If you have questions, feel free to just interrupt. Yeah. What was that? Great question. Perfect segue. The reason this happens is because, or the reason that you still have high availability is because you have multiple monitors. So what the monitors are actually doing is talking to each other all the time. And because I have 3 here, you could have more. Generally, clusters will have like 3 to 5-ish. But they'll all be talking to each other, and they'll generally be on different servers than the actual drives. And what they'll do is they'll kind of like map out all of this general terminology between each other. So, for example, something changes, one of these blocks gets too large, Ceph decides I'm going to split it into 2. The monitors go through like a whole like handshake process, figure out what they're going to do, where the data is going to move, and then they're going to apply it, and they're going to do that entire system. Another example, say for example, one of these drives failed, right? What's the plan now? Well, what Ceph's going to do is going to say, okay, red, orange, and a bunch of other stuff that I didn't include. But these 2 blocks are now missing a 3rd copy, right? So it's going to call them what's called degraded, because they only have 2 copies now, so it's 3. It's going to look at these 2 copies, take all that information, copy all those blocks to a different drive. So basically, the random algorithm is going to update, and that's part of the paper that I referenced. That random algorithm updating without like messing up your entire system is another key part, right? Because you don't want to just move all of the data around as soon as one part of your cache changes. You don't, like, if one drive fails, your entire cache changes, right? But you want to update it so that like these move somewhere else, but also like not too much information is moved around, such that like the drives are still balanced, but also you don't have to spend like weeks moving data around to match. So that's what it's going to do. And then once the drive gets plugged back in, it's going to move the data back into the new drive. Yes.
So those maps that are maintained by the monitors, are those stored on the monitors?
Yes.
Okay.
Do you store a complete map on every monitor, or do you share this somehow?
What was that?
Do you store a complete map on every monitor, or is it somehow?
Complete on every. The whole point is that like, if one monitor dies, the other 2 still have it.
So if you get to a point where you have like 100 terabytes worth of maps, it's a very large amount, then you're kind of
The thing is that you have to maps. That's fine, because percentage-wise, it's still a very small amount. If you have that many thousands of exabytes worth of data, you can figure out a way to store terabytes of maps.
Well, you can, but not necessarily what my point is, of having a full map on every monitor is a limitation.
You can distribute the monitors probably, but like the point, they're not storing data. They're storing like just where the data is, right? That's way less data than the
But you
actual
still have a
data.
cap, which you have every half hour.
Yes, there's
That's
a
what-
practical upper bound to the amount of data that can store the system, but it is more data than you can like reasonably accurate.
No, that's a challenge.
Okay.
Yes, it is. Please produce me a Ceph system where the meta takes up 100 terabytes.
So just cap them randomly what every monitor.
Yeah, but in order for the map to get that big, you have to have enough storage to store that.
Yeah.
Like, please show me your thousands of exabytes of storage cluster that you
Okay,
added
if you're
there,
really
right?
going to handle a challenge, then take the library of Babel, and then
No,
have
no,
a drive
you did.
to abstract the
You
full
said
time
something like
of
that.
Babel. It's a completely different term.
Anyways, I forgot what my next slide was. Right, okay, problem is basically solved. One more thing I want to mention is the maintenance stuff that I was talking about earlier. You have to replace drives. For example, one common process is you want to replace like a smaller drive with a larger drive. Very simple process. If you want pure high availability, you say, I'm about to replace this drive, and then you give it like a few hours. It's going to move all this data to other drives on the same server, because again, you want a copy on each server. So it's going to move all that data out, clear the drive basically, and say, okay, I'm ready. You swap the drives, you say, new drive is in, and it's going to move them all back in. And all of that, like, smooth handling is again done by the mapping. Yes.
So this system, the flaws here, this video, it seems like it would all work very smoothly unless you get into a situation where the cumulative amount of free logical space is less than the size of any single drive.
Amount of. Okay.
Or rather, sorry, actually, no, it would be the amount of physical space. So if say, I have, 1 petabyte cluster, and I have only 1 terabyte, or only like 2 terabytes of space left. And I'm like, oh, I need to pull out.
If you can afford a petabyte cluster, you can afford it, you can buy an 18 terabyte drive.
So, okay, so here's what I'll say to that. Ceph literally, Ceph completely dies, like breaks, if you get to 95% utilization.
Yeah,
90%. Yes.
Does it fail gracefully, or does it?
No, it's just like I don't want to risk writing to it when you're so full because it's like suspicious.
So it like starts with losing right.
Well, what the real issue is that algorithm that's balancing everything. When you're so full, it's going to have to move so much around to handle even like a small change, right?
So performance degrades, but it stays fine.
It degrades a lot, and by 95%, you're basically covered. So it just completely freezes. By 90%, you get like a bunch of warnings, and 85% is like the threshold that you have to stay below. Yes, that is a drawback to this, in that you need a lot of free space in your system to be able to handle a thing like this. You can't be using like 90% of your system.
This is not a unique set problem. CEPH also kind of shows us how to do it on top of
I don't know. I don't know much about the theory behind this, besides like a few papers. But I know there's probably research into like how to distribute data better while also dealing with like maximum utilization problems. Okay. Anyways, so that's solved. Unless someone wants to counterpoint and say it's not solved.
I think I have an idea of how to solve it better, which is
Okay.
you can keep a list of all your drives and how much free space you have on each drive, and store that in a heap. And whenever you need to write something, either new data or when you're pulling a drive out, you pick the drive with the most free space, you write that block, and you move back and move wherever it goes. In that way, you can keep things balanced without having to do any randomization at all. And since you're already storing the full index, there's no need to use hashing to figure out what drive.
Okay, but how do you handle multiple servers?
What?
How do you handle multiple servers, each with their own drives? And fun fact, this algorithm doesn't just handle multiple servers. It's very capable. It handles different racks. So for example, if you have like 20 servers across 5 racks, you can tell it, I don't just want 3 copies across my servers. You can say, I want 1 copy on any of the servers in 1 rack. And that expands to data centers, to like regions.
You can do that if you can write rules as some sort of basic language, what your rules are. Like, maximum, whatever you have. And then pop things off this heap and then re-add them at the end until you pass the drive.
Okay, I don't know enough to tell you whether that will work or not, but you can try.
the DSL intro and I've written it before. I don't recommend it. Generally, it's better to just let Ceph in and that's fine. I don't.
System sounds a bit
aware that what you're trying to do won't work. I didn't quite hear everything you said. I would suggest that a lot of very smart people have worked on this problem, and if
Okay, but
you're
that's not
seeing some
interesting.
obvious,
That's not interesting. There's something wrong with it. What's wrong with it? How can we put somebody else looking at something wrong?
Wait, you should look into it if you're interested in trying to like make this better. It's active research. You should look into it. That's what I will say. Okay. Next thing we need. This thing that I talked about earlier, where you want to actually like scan inconsistencies. I believe CEPH does some of this while it's reading and writing. Like when it writes, for example, does a quick. If it's like, I think the proper thing that it does is if it's like a commonly read or written part, it kind of like runs these operations every like nth time you're reading or writing to it. But also you want to do this just in general, and that process is called scrubbing. It's the same diagram from earlier. But basically what it does is it's gonna randomly, like think cron job type situation. It's just gonna every once in a while look at every single one of these blocks, which by the way there'll be like thousands generally. It's gonna look at each block and it's gonna like compare all 3 copies of it, and it's gonna make sure that the checksums match, that like the data looks similar enough. And if the checksums don't match, it's gonna do that bit by bit comparison to fix the issue. What's that? How does that actually work? Text-based representation. There's 2 types. There's light scrubbing, there's deep scrubbing. Light scrubbing is just, is this the size match? Do the general attributes match? Does everything look generally okay? That by default happens daily, customizable. And deep scrubbing is kind of like looking into the actual object data. Each of these placement groups, these blocks, are split into further blocks, maybe like thousands of those smaller blocks, and this looks at those smaller, these are actually called blocks in CEPH terminology. And like make sure that the checksums match and everything else matches. So that's this process. Now that's solved. I don't know, any other problems you might want to screen out? Hopefully not, because this is like a production system. Now quick software overview. It is. As long as the cosmic ray doesn't bit flip 3 of your drives that have the exact same data.
yes, but if you plug it for the checksum, it's only interaction with the checksum. That means if you only ever write to an LSD, the checksums will always match. But it's not actually doing the kind of comparison between checksum. If an external source like a cosmic ray bit causes a bit flip, it doesn't affect the checksum. Or
Do drives not have like internal checksums that they calculate?
Oh, yeah, you're right. Good one. Which if you're using this, you probably.
But also, checksum functions are designed to avoid that, such that adjacent bit patterns, or like adjacent bit patterns, have different checksums. So in general, like the teaching principle says you can't have like a one-time output. But in a well-designed checksum, any checksum collisions would be very different. The chance of getting
Yeah, so I was the part I'm unclear about is when is the checksum computed, but is it still
Question I do not know.
Is the checksum computed on the block weekly and then they compare the checksums as a way to do a bit by bit comparison? It is just hashed for the sake of performance, or are checksums stored with the blocks on disk and they just read that in?
I think that's informed because a lot of times it's not going to work.
Yeah. My understanding is that the checksums are recomputed when it does this because, or else there's really no point if like your drive starts failing, then like if you just cache the checksum, you're not really checking anything.
Okay, that makes sense.
But I'm not sure on that, so I don't know. Look it up. I don't know if it is true. Okay, so here's the architecture. Question is, what can we build on top of this? Because all we have is data that's split across servers. The answer is a lot. Starting with CEPH, and this is what everyone's been asking about for the past 30-ish minutes, which is now we have a file system on top of this. It's very complicated. I will go into it a little bit in the future. Very easy. But the actual architecture of it is complicated. There's another paper if you're interested in how this worked. And this was also kind of like one of the beginnings of CEPH papers because they were able to build a file system on top of this architecture, which is kind of cool. RBV. Here's another thing you could build on top of this. This is block device. It's basically splitting data into blocks, but not the blocks that go in the hardware level, but the blocks in the software level. and that's useful for running VMs. So generally, Kivu and a bunch of other stuff are really compatible with block devices in general. I believe this is how like VMs actually run in like non-Ceph situations. So this kind of API is basically like very compatible with VMs.
Can you clarify that statement? I mean, this is
I mean, like VMs don't like run on a file system; they run on like blocks of storage, right? So like,
They usually run on QCon true file, depending on like block device on top of it.
You know, it's like,
yes.
on a-
So what I was going to say for that is the QCOW files themselves are kind of like
the QCOW files are a file representation of a virtualized block.
Right.
Yes. Because like, if you're using like props files, creating VMs that way, it does use RDP. So it means that like, how can you get file from the second
Yeah.
wall? It will just create that. Okay. I just usually like
I
It's
think-
important to have more than one of these on the same set cluster without us pre-assigning the ratio of space between.
file system or RBD, which one?
So say you have a single large cluster, and like your university, you want to have both VMs and how.
Yeah, you can have as many of these as you want.
But can you have it? I have a petabyte cluster, and I would say I want 100 gigabytes of data. I want it to just dynamically grow as needed.
That's
Not-
default. They will
Yes,
dynamically.
they're
grow.
only for the
Yes. So you can have. I think one of the file system limitations is that you can only have one Ceph file system, but they also have like some experimental ways where you can make multiple. Because theoretically, like the only limitation is an API limitation. It's not like a hardware limitation. You can have as many of all these. As you want. Sure.
It will work fine. Especially if there's no prefix size. It's exactly the same.
That's assuming you don't want to like.
I'm not prepared to agree with you
Why?
on that. Because, specifically because it's a POSIX file system, and for the
Yeah, I will talk about that a bit more. I'm going to
It's not to be more flow.
It definitely is. And also, CEPH does a lot with like concurrent accesses. So it journals your access to. So for example, CEPH is designed for like 50,000 people trying to write the file system. It can handle that. Your block device. Yes. Well, not file because it's all kind of like primitive data. But yes, it handles some form of like things like on the file system. Like if you're in the same directory and you're dealing with two files, it mostly boils down to metadata of like all the like POSIX file systems.
Imagine the same file in the same directory, I need change, I save, but you're still in your address.
That's just kind of like normal how file system works, which is it just overrides. This is more for like, I wouldn't say same file, but like you're doing stuff that shouldn't affect each other in like the same file system, which if you were to use a file system as a block device would kind of be like annoying to implement yourself.
I mean, maybe you don't really need to go, there are file systems that are.
You could also just put the DXC4 and like NFS or SMB or whatever.
Well, there's that, but also.
You can put an NFS layer on top of it, sure.
But also, like, there are places file systems designed to go on designed to concur access in mind. Yeah, maybe you don't want to use the XP4, but XFS is why you
Anyways, there's one more thing that you can build on top of it, which is object gateway, which this is kind of like S3 buckets, is what you can imagine it as. S3 compatible. So commonly, for example, like the Ceph file system that I set up a few years ago, Ceph file system for like a file system RVD to run virtual machines, and then object gateway to store like log files for like logging clusters and stuff. That's kind of the general idea of what you're trying to get with all these. You can have as many or as few as you want. So initially we didn't have an object gateway. So that's general overview what you can build on top of it. And then final concept before I get into CEPH is CEPH pools. And this is kind of how CEPH implements like all these different stuff that goes on top of it, is it gives each thing a pool. So a pool is just a, okay. Pool is just like a high level group of data. So for example, your file system could have a pool. Actually, CEPH has multiple pools, but we'll get into that later. You can have a pool for all your VMs. You can have a pool for less important VMs and so on. And what that gets you is you can specify per pool replication, which is important because maybe you don't want everything triple replicated. Maybe you don't care too much about some stuff like logs versus some very important stuff like your very like public-facing virtual machines, which you want like complete high availability to. Maybe you want to be like 2 or 3 of them to go down and you're still fine kind of situations.
Does CEPH work with kind of compute time on serving around?
Yes. Mount dot. I think it's just like mount.ceph.
I don't know. I don't know.
But yes, it has a fuse client.
Do you have a timer right now?
Yes, it is. Yeah, it's a kernel module, I believe.
I mean, I'm seeing things in the kernel also should be
Okay. I thought it was cool, which I'm actually remember. I prefer to
if you use it as that, I mean, microkernel, a microkernel is right, so yes, you're right.
Yes, precisely.
Okay. Anyways, I don't want to talk too much about SFS architecture, but here's kind of the general overview. You have 2 of these pools. Again, are just like groups of your blocks that go with drugs. One pool is just for your data, and the other pool is literally just to handle all the POSIX and metadata stuff you've got going on. The reason you have this set up is because you want one like journal together that like journals together all your reads and writes for the file system, and that goes into like the concurrency stuff I was talking about with like multiple people accessing a file system. And you also want the ability to have multiple of these MDSs, which next acronym, there are like 20 of them. But MDSs are metadata servers, and they literally just are only for the file system, not for like anything else of stuff. And they just handle like a subset of the clients and what all the reads and writes they want to do. And they journal them together and then apply them to metadata. So overall, I did not explain that too in depth, but anyone have questions? It does feel like an unnecessary computer architecture.
If you can do a better job, then go right. If your code is simpler and you also write it in a bunch of how less fewer bugs and everybody put it up.
I mean, I suppose I can see how they're moving at a massive scale. This might make sense, but like, this just seems unbelievable.
Another main reason that I didn't really touch on is that you also want the MDSs to have failover in case one of them breaks, which does happen because they're all services and you want to like account for anything breaking. So you're gonna have to stand back on this one.
Well, another way you can do that is if you have some sort of locking scheme back in your block player and then store your file system in one of the blocks. That way you avoid when you have.
Okay, sure, but now you have a locking scheme.
Yeah, I was going to say, I assume the goal is to avoid it.
Yes.
But you're going to have a locking scheme in your MBS server anyway.
No, you won't.
Another way you can do that is you could expose in the API you fill in how to optimize it, a way to attach metadata to a block, and the metadata is a locking scheme. You have to have that metadata connected to the blocks themselves. So just add like a user field inside the block metadata.
Okay, I would again say for that, read the paper because I don't know enough to answer that question. But I know that this is a.
You are like basically just, I think, moving the functionality of the into the file system driver. Whether or not that's better, I think is debatable.
It's better because they don't have separate MBS.
Maybe.
But good abstractions have as much as possible and simple as possible abstraction. So like a traditional like normally if you count is extremely complicated inside. If you have like 4 system calls here, it's very simple.
There are like
Yes,
There are like.
there are more now. I think like there are
Like,
ones.
operating system calls.
You know what I mean. There are more now. Initially there were like
Yeah, for like 10 minutes, but it will move up to like 30.
you still can use those for like this and that. Whereas this, it already plays, you have to have those things. Having like an opt-in paper is not right now. I think more easy to do it.
I in principle would agree with you. I would, if you can some kind of asynchronous IO to the APSs, and they're not a little bit more freedom in how you design your walking speed, you might be able to achieve better overall performance, and that might, at this scale, and as a small percentage incremental improvement in performance, might genuinely be worth the effort.
Or it's all for the same project, so you just design it all together.
I think we need to move on.
Let's resume.
Okay, I don't have too much left, don't worry. But CEPH, this is what people use. So, I mean, the general idea is like, if you think of something better, you can write a paper on it and probably get it somewhere. But this is kind of like, they've written a paper on it, it is like peer reviewed, it is like a proper implementation of the file system, and it works. And another diagram where now you have the metadata server talking to the monitor to do all your metadata stuff. And then all your data goes through a separate like route. So this is kind of like the final architecture, including a file system, if you think of it that way. And clients are talking both to your metadata server and your monitors. Final little tangent is authentication. Now, from my experience, some clusters implement this, some just don't. But Ceph does support native authentication. Reason being, not everything is a file system. Again, you can also have like VMs and other types of data stored here. So you can have authentication to access like literally any part of data, and you can specify that. You can say like, this tool needs authentication. You have to be logged in as one of these 5 users and so on. So it has its own authentication scheme. Here's kind of a diagram of like the flow, which is standard authentication to access stuff. Think like Kerberos or so on.
Do they integrate with like the horrors or big communication like LDAP, for example? Or do they
Great
control
point.
the standard?
So it does not. But if you want LDAP and Kerberos, you can use NFS, because you can literally very simply put NFS on top of CEPH. It's like native. And that's normally used for like if you have public facing stuff. So generally all the Ceph authentication and using with the file system is used for internal. So for example, the setup that I came up with was you have virtual machines that mount the Ceph file system. They're completely different blocks of storage. But now you have a triple replicated file system so that in case your virtual machines, you want to do stuff with it, you're fine. And then you have virtual machines that mount them, and you have, say, like other systems that are not on Ceph, for example, like physical servers, also mount the file system. And then now you have a file system for all your data, and then you have servers for it. But if you want to go external, you want to say, let people outside the network mount your drive, for example. Obviously, you're going to have to like share it outside the network and so on. But what you normally use for that is NFS. You set up an NFS mount, for example, in like a subdirectory of your Ceph file system. So for example, like /NFS/ everything else. And then that entire subdirectory would be NFS shared to wherever you wanted it to be shared. And that's where you get bypasses to authentication. You can do cool stuff with like mounting, auto mount, and so on. That's a whole nother.
So does that mean that the Ceph FS has its own NFS server? Or does that mean you can virtual machine or physical server from it?
You have a service.
Also, it exports that just like over using normal like virtual files.
Yes, you have a service.
That's
So,
gonna be simple.
I mean, not really.
What's your
I mean, compared to the rest of it, it'll be.
I'm gonna say, I promise, when you're creating an FS share, the slowest part is almost always the network.
Well, in this case,
Right, right.
you still have a network bottleneck because instead of if you have like many CFS servers, you have many clients. You would also have to have just as many NFS copies or available network, not many more network.
And that's another thing. It can do high availability with the NFS client, and it has load balancers between the clients, and you can go as far as you want into this. So like,
So you're saying
yes.
CFS is all NFS implementation as opposed to just relying on virtual files.
Yes, it has its own implementation.
Okay, well that's more reason. That's my question.
And it has its own services and so on. I was going to do a quick demo. Maybe I will later. But for first, any questions? Because it is 7. So if anyone wants to stay, I might do like a 5-minute demo after. Yeah.
What kind of snapshots does it support?
I did skip that. Yes. I think they're like some own proprietary implementation. They're not
Is it
proprietary.
like, is it, if you do it on 7+, is it like for the entire file system, or is it per file?
You can have it per file.
Okay.
You can have it per file. Copy on write. So it's not going to like store your entire
Yeah.
subdirectory. It's just going to store the state of it and then all the modifications in it. Any other questions?
You said you deployed this, right?
Yes.